There's this hidden language that the entire universe speaks. It's not math, exactly. It's something even more fundamental. It's the language of measurement, and it's how scientists all around the world can actually agree on what's real. So let's dive in and learn to speak it.
Just for a second, imagine this. What if you tried to buy a kilogram of coffee, but a kilogram in France was different from a kilogram in Japan? Or, even crazier, what if the engineers building a rocket were using a different meter than the scientists who calculated the trajectory? I mean, it would be total, absolute chaos, right? And that little thought experiment really gets to the heart of why we need this stuff. It's not just nice to have, it's completely essential.
So how did humanities solve this massive potential for chaos? Well, the answer is an idea so basic, so fundamental, that we pretty much take it for granted every single day. The idea of a unit.
When you really get down to it, a unit is just an agreement. That's it. A meter is a meter because a bunch of people, specifically scientists, all over the world agreed that this is how long a meter is. It's a shared reference point, a common ground that lets us start building our description of the physical world. And look, this isn't just some abstract thing for physicists in a lab. Think about it. Global shipping, the computer chip in your phone, satellites beaming down GPS signals. Literally none of that could happen unless everyone is speaking the exact same language of measurement. It's like the invisible grammar holding our entire modern world together.
But yeah, this elegant system we have now, it didn't just appear out of nowhere. For a long, long time, the world of measurement was, to put it lightly, a complete and utter mess. It was a jumble of competing systems that just created confusion.
I mean, you had all these different teams playing by different rules. You had the CGS system, which is short for centimeter, gram, and second. Then there was the FPS system, or the British system, with its foot, pound, and second. And even another metric one, the MKS system, for meter, kilogram, and second. A scientist in one lab could be using grams, while another was using pounds. It was a total nightmare, inefficient, confusing, and just asking for mistakes.
So finally, the global scientific community got together and basically said, okay, this is ridiculous. We need one system to rule them all. And that's what they created. We know it as the SI system, or the International System of Units, which comes from the much fancier-sounding French Système International d'Unités. This became the gold standard for all of science and technology.
And this is it. This is the heart of the whole thing. Everything, and I mean everything we can possibly measure can be broken down into some combination of just these 7 fundamental units: the meter, the kilogram, the second, and so on. They're like the primary colors of reality. You can mix them together to create any other unit you could possibly need. Okay, so we're all speaking the same language now. Great. But that only solves half the problem. Now we have to deal with the problem of imperfection. It's not just about what you measure, it's about how well you measured it. How do you communicate that?
This quote really hits the nail on the head. No measurement is perfect. Ever. There's always going to be some tiny bit of uncertainty. So scientists needed a system to bake that level of precision, or imprecision, directly into the numbers themselves.
And the tool they came up with is called significant figures. Honestly, you can just think of it as a secret code built into every measurement you see. It tells anyone who's reading it which numbers you're absolutely sure about. And it points to the very first number where you start to get a little bit uncertain. It's the language of precision.
And this right here is a perfect example of why this matters so much. When you see 4.700 meters, it means something completely different than 4.7 meters. Those 2 extra zeros on the end aren't just for decoration. They're a signal. They're telling you, hey, I used a really, really good measuring tool, and I am confident in this measurement all the way out to the thousandths place.
Okay, I know, rules can sometimes be a drag, but here's the quick and dirty on how to count these things. Any number that isn't a zero is always significant. Easy. Zeros that are sandwiched between other numbers, like the 0 in 502, they count 2. Now, zeros at the beginning, like in 0.05, they're just placeholders, so they are not significant. But, as we just saw, those trailing zeros after a decimal point, oh yeah, they are absolutely crucial. They are very, very significant.
And if you really want to be crystal clear and avoid any mix-ups, especially with huge or tiny numbers, scientists have a go-to tool, scientific notation. When you write 4.700 times 10 to the third, there is zero ambiguity. Everyone knows you have 4 significant figures. The precision is locked right in.
All right, this last part is my favorite. So we've got our shared language, we know how to talk about precision, but
how do we know if our scientific sentences, our equations, are just complete nonsense? Well, physics has this absolutely beautiful built-in solution.
It's this really cool trick called dimensional analysis, and you can honestly think of it like a spell checker for physics. The secret is to completely ignore the numbers for a minute and only look at the fundamental quantities you're dealing with, the dimensions like length, mass, and time. It's a surprisingly powerful way to check your work.
The logic behind it is, well, it's just common sense, really. You can add one apple to two more apples and get 3 apples. But you can't add an apple to a bicycle. It just doesn't make sense. And it's the same in physics. You can add a length to another length, but you cannot add a velocity to a force. The units, the dimensions, have to match up.
So, let's put this spell checker to the test. We'll take a classic, famous equation from physics, the one for energy. On the left side, we've got kinetic energy, which is 1/2 times mass times velocity squared. And on the right, we've got potential energy, mass times gravity times height. So the big question is, do the dimensions on both sides of that equal sign actually match?
Okay, let's break down that left side. The dimension for mass is just mass, which we write with a capital M in brackets. Velocity is distance over time, so its dimensions are length over time, or Lt to the -1. But remember, the formula squares the velocity, so we have to square its dimensions, which gives us L squared t to the -2. Put it all together, and the left side has the final dimensions of m L squared t to the -2.
Now, what about the other side? Mass is still just m. Gravity is an acceleration, which is how fast your speed is changing. So its dimensions are length over time squared, or Lt to the -2. And height, well, that's just a length, or L. So when you multiply all of those together, what do you get? You get mL squared t to the -2. Exactly the same thing.
And there you have it. The dimensions on both sides are identical. The equation totally passes our spell check, it's dimensionally consistent, and that's a really, really good sign that it's a valid, meaningful equation in physics.
So when you step back and look at the whole picture, you see what's really going on. Measurement isn't just about writing down numbers. To solve the problem of agreement, we needed a shared language, our SI units. To solve the problem of imperfection, we needed a way to talk about precision, and that's significant figures. And to solve the problem of nonsense, we needed a grammar, a logical spell check like dimensional analysis, to make sure our equations are even coherent in the first place.
But this leaves us with one last big question. This spell check, this dimensional analysis, it's great at telling us if an equation is definitely wrong. But it can't tell us if an equation is right, and it certainly can't tell us if it's a beautiful, profound insight into the nature of the universe. That takes something more. So, if this is just the grammar of physics, what does it take to be a true poet? That's something to think about.